Involved in the triaxial compression test are very similar to those of the unconfined compression test. Because the machine we used was the same, our proving ring constant will be the same, and our deflection dial gauge least count will be the same. And because the dimensions of the cylinder were also the same, our volume and area will also be the same. One of the differences in the table we make is that we also have to add a column for cell pressure. This indicates that these readings were performed under this value of sigma 3. And then the rest is pretty much the same. Our deformation dial gauge readings, our load dial gauge readings, and then the same calculations that we performed in the unconfined compression test. Multiply deformation dial gauge readings with the least count 0.01, and you get the deformation. Strain is equal to change in length over total length. The correction factor is the same as we determined for the previous experiment in the unconfined compression test. So the correction factor will be the same, so the corrected area will also follow the same pattern, and load and stress are the same. Load is by getting your is we get load by multiplying our load dial gauge reading with our proving ring constant, and by dividing our applied load with the corrected area, we get our stress. So I've highlighted the key points, the peak points of stress achieved for each cylinder. For 50 kPa, for 100 kPa cell pressure, and for 150 kPa cell pressure. So one thing we do that's pretty straightforward that we did in the previous experiment as well, we make a graph of stress versus strain. On our x-axis we have our axial strain, on our y-axis we have our stress. So what we just have to do is we have to select the data for axial strain and our stress, and we get 3 curves because we have 3 cylinders. So this is just a side-by-side comparison for all of them. Next, what we also have to do is we have to draw our more Coulomb failure envelope. And because this will have 3 more circles side by side on the same graph, what we do is for the cell pressures involved, we note down the cell pressures involved, and half the peak stress value that we calculate, that it will be our radius, like our radius for the cell pressure at 50 kPa will be half of 506, so that's 253. For 100 kPa, it will be half of this, and for 150 kPa, it will be half of this. So I've noted down the radiuses for each of these. Then what we just have to do is once we do the set of degrees and convert them to radians, then we have to get XY coordinates for each of our values, 50 kPa, 100 kPa, and 150 kPa. So how we get this? Now here it's slightly different. The formula is for the most part the same. However, the difference is that in our x values, first it used to be r plus r cos theta, the radius plus radius into cos theta. But here, because that was when the cell pressure was 0. Here, because we also have 50 kPa of sigma 3, so it has to be 50 plus r, or 50 plus the radius plus radius cos theta. So as you can see, K32 is 50, and our radius is L32. So over here, 50 or K32 plus L32 plus L32 cos theta, which is our value over here. For y, it's just the same r sine theta. You don't have to add anything to that. So Over here, when we do 50 plus 253 plus 253 into cos of whatever value you have in radian, then you drag that down, you get your entire x values, and then in y it's just 253.36 sine theta. After that, you do the same for 100 and 150 kPa, where it will be now 100 plus r cos theta for your x values of 100 kPa, and 150 plus r cos theta for your 150 kPa x values. And the y values will go on the same format of r sine theta. So here are your radiuses, cell pressures, and when you do this, you will get, when you plot these, you will get these three Mohr circles. So these three Mohr circles are showing your value for, and each value for 50, 100, and 150 kPa. So now, one thing you have to realize is because that this is an unconsolidated, undrained experiment, and we are not measuring pore water pressure through the cylinders or back pressure or any of the other uh, parameters. We are just measuring the deformation and the load applied. Because of this, these Mohr circles are based on a total stress value rather than an effective stress value. So the C and phi that we will get from these will give us will be total stress shear parameters rather than effective stress ones. So how we get this is now we have to draw a tangent line for these circles. When it was unconfined compression test, we just had to draw a horizontal line because there was a single circle that would touch the top of the, or the peak of the Mohr circle. However, because now there are three circles, what we have to do is we have to draw a tangent line that touches each of these Mohr circles, a line that is tangent to all three circles. So for the tangent line, you can now at one point the tangent line has to intersect the y-axis, so at that point our x will be 0. And for the other point, I'm just taking a value that is over here, 550. And now if you have this on a graph paper, you can easily just draw a tangent line, or if you're on Excel, you could say draw a shape line like this and then move it until it touches all the points, and then you could just guess what points those lie in to draw a proper line. Or what you can do is just using a bit of trial and error, say if it was 150 and 350, our x is our first point would be 0 and 150, and the second would be 550 and 350. So if we draw a line for that, we'll just add a series. Our x values are this, and our y values are this. Now you can see here that the line is not touching the edges of the circles, it's rather acting like a chord for them rather than a tangent. So what we have to do is we will adjust the values of the y axis in the tangent line. So if we say make it 155, we can see that our line is starting to move a bit. Or if we make it 160, and then the other one, if we try 355 or 360, When it's 360, we can see that now the line is acting as a tangent for all the circles. It's touching the blue circle, the orange circle, and the gray circle, 50 kPa, 100 kPa, and 150 kPa. So now we have a line that is a tangent for all the circles. So next what we will do is we will just add a trend line and then display the equation of this line. So the equation is displayed. Our intercept is 160 and our slope is 0.3636. Okay, so now what we have to do is we know that our C is equal to 160. So our phi is now equal to our phi will be equal to tan inverse of the slope of our line. So tan inverse our line is the slope, or m, is 0.3636. So if we use this in Excel, this will give us a value in radian, which is why you also have to convert it back to degrees by multiplying by 180 and dividing by pi. So 0.3636, which gives us a value of 19.98 degrees. This is our phi, and our C is 160. And that's all there is to our calculations in this experiment.